So what we're going to do now is relate the antiderivative to a concept that's going to be dealing with areas under curves. So we've seen the derivative representing some type of rate of change. Integral calculus is going to study the accumulation of these units as this rate is changing. So we can study it graphically, and then we'll relate it to this antiderivative at the very end. So let's first work with an example that's relatively simple that you don't need calculus to go through, but then we'll be able to see how to relate the calculus in hopes to make this concept solidified. So a skateboard company determines that for the first 50 skateboards they produce, it's going to cost $40 per skateboard. We want to see what the total cost to produce 50 skateboards is going to be. So this is relatively straightforward. $40 per skateboard, $50 boards produced. You just multiply the two. But in terms of what we related to this before, the marginal cost is exactly this rate of change. So the derivative of the cost function is going to be 40. Every single one is going to cost us $40 per skateboard. And that's going to be true when x is between 0 and 50. So our total cost is just the product of those two. It'll be $2,000 to produce these 50 skateboards. But if we think about this graphically instead and plot that derivative function, c prime of x is just 40, so it's just going to be a straight line. And if we look at the area underneath this derivative from 0 to 50, all that is a rectangle. The width is 50, the height is 40, you take the product of the two. So the area under the marginal cost function is going to tell us how much it costs to produce 50 skateboards. So in this case, you obviously don't need to do that to figure it out, but when you have more complicated functions, we know how this area relates to this accumulation of the cost, the profit, whatever it is in particular. So let's look at another example. Poise Inc. has a marginal profit function given by p prime of x is negative 2x plus 80. So this rate is going to be dollars per unit. So this means that the rate of change of total profit with respect to the number of units produced, which is x, is this rate. We want to find the total profit from the production and sale of the first 40 units. So this derivative is just a line, so it's not too bad to plot. It goes through 0, 80, its slope is negative 2. So you can plot this from 0 to 40 because we want the first 40 units. So if we want the total profit, we just find the area underneath this curve. So this is not something that has a constant profit from each one. The more you produce, the less profit you're going to make. So you can't use the same algebraic approach as before. But because the area is nice, it's just a triangle, the area under the curve will give us the profit from 40 units. And the profit is just a triangle, so it's 1/2 times the base, which is 40, times the height, which is 80. So our profit from the first 40 units will be $1,600. Now suppose that the same skateboard company has a marginal cost from the first problem. So the first 50 boards cost you $40. Between 50 and 125 boards will cost you $30 per board. And then 125 to 150 will cost you $25 per board. So we want to find the total cost of producing 150 skateboards. Now, this is a piecewise function. So on the first piece, our height is going to be 40. Then our next piece from 50 to 125, it's going to cost us 30 per board. And then finally on the last piece, it's 25 per board. So if we want to find the total cost, I need to find the area under this curve. But because we have these varying heights, it's going to be a little bit easier to break it up into pieces. So what we're going to do is look at those 3 different sections on their own. We'll find the area of each, add them together. So for this first one, the length down here is going to be 50 and the height is going to be 40. So A1 is 40 times 50, which is 2,000. If we look at A2, it goes from 50 to 125. so the length is 75, and the height is going to be 30, so the area A2 is 2,250. Finally, on this third one, it's for 25 boards from 125 to 150, and the height is 25. So A3 is 25 times 25, just 625. So our total cost is just the sum of these three areas, so it would cost $4,875. So this process really leads to an idea that's called Riemann summation. So it's just named after a mathematician whose last name was Riemann. So when you don't have a nice geometric shape, you can't do this process. If you think of your exponential functions, your logarithmic functions, second degree polynomials, third degree, whatever degree you want, you don't have those straight lines that are rectangles, triangles, whatever it may be. So what we can do instead is get an approximation for the area by using just rectangles. So let's look at a particular thing. Suppose we want to find the area under the function f of x over some interval from a to b. And let's decide to use 4 rectangles to approximate like we have in the picture. So in this case, I want to use 4 rectangles of equal width. And if I want the width, there are going to be some x values here, x1, x2, x3, x4, and I'm going to use the function to figure out my height. So each one of these will be exactly the same width, and the height will use each of these endpoints. So this would be the function evaluated at x1, function evaluated at x2, x3, and x4. So the height will be the function values, and the width will be some set constant. So if you want the equal width, what we can do is we can take the total length of the interval divided by the number of rectangles you want. So we're going to call each of these delta x. And what delta x equals is the length of the interval divided by the number of rectangles. So in our case, 4. So the length up top, how many pieces you're breaking it into. We can then use that left endpoint to approximate the height. And then the area under the curve is going to be just the sum of these smaller rectangles. So this first rectangle is the function evaluated at x1 for the height times the width, which is delta x. For the second rectangle, the width is again delta x, and the height is the function evaluated at x2. For the third rectangle, the height is the function evaluated at x3 times delta x. And then finally, for this fourth rectangle, it's the function evaluated at x4 times that same equal width. So if you do more rectangles, it gets a little bit messy to go ahead and write. So we have another way to write this repeated addition. It's called summation notation. So if you look, this delta x is going to stay the same. The function is going to get evaluated at some point. So the only thing that changes is this index from 1 through 4. So what we use is a Greek letter that's called sigma to represent we're going to sum up. We're going to start at I equals 1 to indicate this first point here. And then we're going to stop at 4. And that's where we're going to end. The index, this I, is changing from 1 to 4. And then the delta x just stays consistent in each one. So the idea is you start by plugging in I equals 1. You get the function evaluated at x1 times delta x. Then you plug in I equals 2, which gives you that second endpoint. I equals 3 for the third endpoint. I equals 4 for the fourth endpoint. So if we look at a simpler example, if we want to sum up from I equals 1 to 6 of 2 to the I, the 2 stays constant every single time, I is going to change. So you start by plugging in I equals 1, so you get 2 to the first. I equals 2, which is 2 squared. Add to that when I equals 3, which is 2 to the third. Add when I equals 4, I equals 5, I equals 6. So it's a condensed way to write this summation when only one thing is changing each time. So we can use these Riemann sums to approximate the area underneath a function because we can split it up and use the function outputs to get an approximation for the height. So let's work with a specific function. We're going to find the area under the graph of f of x equals x squared plus 1 over the interval from 0 to 5 by first using 5 rectangles of equal width, and we're going to use the left endpoints to get the height of the rectangles. So we've got our function here. What we need to do is we need to figure out what is the width of each of my rectangle. So we want to find that value of delta x. From 0 to 5 is length 5. So we take 5 divided by the number of rectangles. Every single one is going to be length 1. So each one of these down here, this will be a rectangle, 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 rectangle. That'll be our 5. And so what this will look like, if we go ahead and break it up into 5 equal strips, on each one of these, I'm going to approximate the function, or approximate the area using a rectangle. So what we have is the area is going to be about equal to this Riemann sum when we sum up from 1 to 5 of the 5 rectangles. This will be the height, this is the width, which in this case the width of every rectangle is 1. So on this first subinterval, the length is 1. The height of the rectangle is going to be the function evaluated at 0. So we take the product of those two. On the second subinterval, the length is still going to be 1, which is our delta x, and the height will be the function evaluated at 1. On the third interval, the length is 1, the height is the function evaluated at 2. On the fourth, the length is delta x, or 1, and the height will be the function evaluated at 3. And then finally, the height on this last one will be the function evaluated at 4. So you're just going to plug in all these x values to the function to see what the height is. F of 1 is 1, f of 0 is 1, f of 1 is 2, f of 2 is 5, f of 3 is 10, f of 4 is 17. And then delta x is 1 for every single one. So those are the widths of our rectangles. So if you add these together, it gives us an approximation for the area. So the area is going to be about 35. And what you may be able to notice is from this picture, I have a lot of blank space. Every single one of these does an under approximation for the area. If you used a different endpoint, you might get an over approximation. So we use the left endpoint, but maybe if you want to use the right. So from 4 to 5, maybe instead I would use 5. This would be my rectangle that would approximate. On this interval, I would use 4 to get the height, and it would give me an over approximation. We would use 3 here. Again, it's over. 2 here is over. 1 here would be over. So you'd still get an approximation for the area. It'll just be an over estimate instead. Okay? So let's try it again, but now using 2 rectangles, and we're going to use the left endpoints. So my length of my interval is still 5, but now I'm only using 2, so each rectangle is going to be a width of 2.5. So we break this directly in half. So 2.5 is my cutoff. I'll approximate the area from 0 to 2.5, and then 2.5 to 5. So this will be what our approximation will look like. The length will be 2.5. On this first interval, we'll use 0 to get our height. On this second interval, our length will still be 2.5, but now I'm going to evaluate the function at 2.5 to get the height. So that's what that point would be. So our area is going to be approximately equal to this Riemann sum. We'll go from 1 to 2 of our function at the left endpoint times that width, which is delta x. So our left endpoint is 0 on this first interval, and then on the second interval, we're using 2.5. So if you plug those into the original function, f of 0 is 1, f of 2.5 is 7.25, and then delta x is 2.5. So you get an approximation for the area, which is 9.75. So you can see we did pretty much the same thing in both of these, but in one case we used more rectangles. We got an area of 35. In the second case, we used 2 rectangles and our area was way lower. It was 9.75. And the reason for that is we have a lot of blank space that's going on in here. If I were to use 10 rectangles, I'm going to make my error be less because I'm going to have more space underneath, or less space underneath. If I used 1,000,000 rectangles, it would be even better because those strips would be so small that they're going to be super close to that function. So this leads into what the actual area under the curve will be. We're going to let the number of rectangles approach infinity, and that's going to lead into this definite area. So we're going to relate it to the antiderivative in the next section, but what we want to think about now is if we have a function y equals f of x, which is continuous and non-negative over an interval, the definite integral is the limit as n approaches infinity of those approximating Riemann sums. So the main idea is the area is going to be exactly equal to the limit as n goes to infinity. So this n is the number of rectangles. We stopped at 2, we stopped at 4, but now we want to take as many as we possibly can to the point that there's going to be no error. So what this is our definite integral. It goes from a to b of f of x dx. And we know how to integrate. We've dealt with that before. It's going to deal with the antiderivative, and we're going to see how to actually deal with these bounds in the next section.